Every video about interstellar travel obsesses over the same number. How fast can you go? Voyager, Parker Solar Probe, laser sails pushed to a fifth of light speed, but almost none of them mention the moment nobody plans for, arrival. Because in space, slowing down costs exactly as much energy as speeding up. Getting up to speed was never really the hard part of a single light year. Stopping is. Before any of that matters, you have to leave, and even that is brutal. To break Earth's gravity entirely, a rocket needs escape velocity, about 11 kilometers per second, faster than a bullet. That's just the opening move. The sun's gravity keeps pulling long after launch, and the first few million kilometers feel like a slog for exactly that reason. It took the Voyager probes decades just to clear the outer planets. Getting free of one ordinary star is already a multi-generational project before a single light year has been crossed. And leaving doesn't mean what most people assume. Where does the solar system actually end? Not at Pluto. That's a myth. The heliosphere, the bubble the solar wind carves out, reaches roughly 120 astronomical units before interstellar space takes over. Beyond that lies the Oort cloud, and here's the part almost nobody corrects. It isn't a cloud. Trillions of icy bodies exist out there, but they're spread with roughly 50 million kilometers between neighbors. Picture a single grain of sand, then the next one, a continent away. The Oort cloud is closer to a sprinkle than a swarm, and estimates put its outer edge as far as a full light year, some say 2, meaning the very journey this video is about might not even clear our own backyard. Between the stars, there's essentially nothing to look at either. An average cubic meter of interstellar space contains less than a single atom. Fly for years, and the view outside barely shifts. No planets, no landmarks, just stars creeping across the sky over the span of decades, indifferent to how fast you think you're going. Chemical rockets, the only propulsion humans have ever ridden past the atmosphere, are hopelessly unsuited to this. Even efficient ion thrusters take enormous stretches of time to build meaningful speed. Now the real numbers, 3 of them, none theoretical. Voyager 1, the fastest thing humans have launched past the outer planets, has been flying since 1977, almost 50 years, and moves at 17 kilometers per second. At that pace, 1 light year takes about 17,000 years, roughly the distance from the first cave paintings to right now, just to cover the first step. The Parker Solar Probe takes a completely different approach, diving close to the Sun and letting its gravity do the accelerating, hitting nearly 700 kilometers per second during its closest flybys, the fastest speed any human-built object has ever reached. Even so, a light year would take about 430 years, longer than the probe's own mission by centuries. Breakthrough Starshot, a concept, not a working spacecraft, proposes laser-driven sails accelerated to 20% of light speed, using ground-based lasers instead of onboard fuel. At that speed, 1 light year takes roughly 5 years. But that's a probe the mass of a postage stamp, not a ship, not a person. Here's what every one of those numbers quietly assumes: that arriving means flying past, not stopping. Actually slowing down changes everything. Kinetic energy scales with the square of velocity, so decelerating at the destination doesn't just double the fuel bill, it squares the mass ratio. A mission needing roughly 100 kilograms of fuel per kilogram of payload to reach cruising speed can suddenly need 10,000, because the deceleration fuel has to be accelerated too, the entire way. Engineers have floated magnetic and electric sails that break against the thin interstellar medium instead of carrying propellant. One model design, a craft weighing 4,000 kilograms and cruising at 8% of light speed, still needed over 50 years just for the braking maneuver. Physicist Robert Forward once proposed a staged laser sail that could decelerate itself without any hardware waiting at the destination. none of it has ever flown. There's an old workaround for the fuel problem too. Scoop up hydrogen along the way instead of carrying it all from launch. Interstellar space holds roughly 1 hydrogen atom per cubic meter, and in theory a large enough collecting funnel could gather propellant as the ship flies. The catch is relative motion. From the ship's perspective, that hydrogen isn't sitting still, it's rushing toward the hull at cruising speed, carrying serious kinetic energy of its own before it's even useful as fuel. The scoop doesn't remove the energy problem, it just relocates it to the front of the ship. Time dilation. Sounds like the loophole that fixes all of this, and it doesn't. Not for stopping. Special relativity really does let a ship's onboard clock run slower than Earth's, so a vessel holding a constant, comfortable 1g of acceleration could in principle cross vast stretches of the galaxy within a survivable span of crew time. But that math assumes the engines can also decelerate at 1g the whole way down, which loops straight back to the same mass ratio problem. Time dilation changes who experiences the years. It does nothing to shrink the fuel needed to shed the speed once you arrive. Even a working sail still has to survive the trip. At relativistic speeds, interstellar gas atoms bombard the hull, and dust grains, some no larger than a grain of sand, strike with enough energy to blast craters and melt material. Researchers modelling Breakthrough Starshot's sail found the damage manageable, mainly because large grains are rare, not because the physics is forgiving. Radiation adds another layer. No planetary magnetic field to hide behind, just years of cosmic rays hitting unshielded tissue, with no practical shielding yet capable of stopping it. And if a crew were aboard, contact with home becomes symbolic. A radio signal takes at least a year to cross a single light year one way. Real conversation stops being possible almost immediately. So what would you actually see, assuming you survived all of it? Barely anything changes. Without acceleration, motion feels identical to standing still. No sound, no push, nothing but a slow drift of starlight over years. The constellations stay recognisable for most of the journey. Only near a destination star does it begin outshining its neighbours, while the sun behind you fades quietly into just another point of light among thousands. And that destination is still nowhere close. Proxima Centauri, the nearest star, sits 4.2 light years out, so 1 light year is under a quarter of the way there, and Proxima is the lucky case. Most naked eye stars sit 10, 50 or 100 light years off, distances where a single light year barely registers as progress. Zoom out further to the Milky Way's 100,000 light year span, and even our own small corner of it, the Orion Arm, holds thousands of stars, each one farther away than a single light year could ever cover. A light year isn't the finish line, it isn't even the driveway. That's the real shape of the problem. Not just reaching a speed, but shedding it again at a destination a single light year barely brings into view.